Math 504 Advanced Calculus, Chapter 2, Exercise 2.10. My topic is to prove that a convergent sequence is bounded. Sequence is definition basically exactly what you had expect. The idea behind this proof putting string 4. Let En be the convergent sequence and then En is bounded. Let us say an, sum of the sequence E, and E is our convergent. Let's say A, the definition of the convergence sequence. We could pick any positive number, epsilon, that we want. Let us say epsilon equals 1. Then, follow the definition, then exists some natural number, big N. So, for all these terms sequence after the big N terms, we have that those terms of the sequence are written in one of the limit A. So, the absolute value of En minus N less than 1, again, this is the definition of sequence En convergent A. So this absolute value inequality equivalent to the value bar. To writing negative 1 less than E1 minus A less than 1. So absolute En minus N less than 1 and negative 1 less than En minus A less than 1, only this description proving that the equivalent is very important result. We add A through this inequality to have A minus 1 less than An less than 1 plus A. In other words, we have the lower bound, which is A minus 1, and the upper bound is 1 plus A. For all terms of this sequence after the big N terms, we guarantee that all terms of sequence after the big N terms. A, the certain point are bounded between A minus 1 and A plus 1. This only one finite number of terms left of the sequence to count for. So we should able to adjust our argument to make sure that works for all terms of the sequence. So our lower bound is A minus 1 and the upper bound is 1 plus A. So the U or the upper bound A plus 1, we know that this is the upper bound for all terms of sequence after the big N terms. Similarly, we start lower bound A minus 1 for the similar reason. By this definition of convergent sequence, we can show that this U equals 1 plus A and L equals A minus 1 works together for every terms of sequence of the big N terms. So that will happen that we accounted for all first big N terms of the sequence. E1, E2, and so on, E and this is possible of this the bigger. So E plus 1, on this case, we increase our upper bound U. Accordingly, in order to do that, we use the maximum function so that the upper bound E plus 1 might be worked. So guarantee that the upper bound who works for terms of the sequence. What we need to show that the sequence bounded, so U or the maximum E1, E2, and so on, En 1 plus A. So for all this number of the upper bound or the maximum, for L, one of these number is E1, A2, and so on, An, A minus 1. This case is decreasing the L accordingly. To make sure that we'll still have the lower bound of L, so the L a minimum of E1, A2, and so on, EU and A minus 1 is our minimum or the lower bound. So that the U upper bound of the sequence is greater than or equal to in every terms of the sequence, and L is the lower bound of the sequence is less than or equal to in every terms of the sequence. So we have L less than or equal to En less than or equal to U for every terms of the sequence of En. For recap on how this equally hold of the sequence, En less than or equal to big N, big N terms, then U is the maximum of the set contents of all terms. Similarly, U is the greater than or equal to A1, A2, and so on, En 1 plus A. So the L or the minimum is the less than or equal to those E1, A2, En, and A minus 1. So the N less than or equal to big N, remember that this counted for those E1, A2, and E and so on, E and E plus 1 and E1, A2, and so on, E and A minus 1. So the in less than big N is the other terms to N greater than big N terms is selected especially using the definition of convergent sequence to ensure that En in the following terms lie between E minus 1 since 1 plus E is the maximum of U, then 1 plus A, L is the minimum of E minus 1 of all the sequence. So we found the upper bound and the lower bound lie between U and L. So our sequence of En is bounded. This proves that convergent sequence is bounded. And thank you.